What if you could find the exact speed of a falling apple at a single perfect instant in time? I mean, it sounds kind of impossible, right? Well, the tool that makes it possible is one of the most foundational ideas in all of calculus, the limit of a function. And in this explainer, we're going to demystify it.
Okay, so here's the plan. First, we'll look at a function that has this mysterious hole in it. Then, we'll build up a really solid intuition for what a limit actually is. We're going to see what happens when the paths don't meet up, and when functions just shoot off to infinity, and finally, we'll see why this one single concept is the key that unlocks pretty much all of calculus. All right, let's get started.
So to really get a feel for this, we are not going to start with some dense textbook definition. No. Instead, let's kick things off with a little puzzle, a function that has a very specific, kind of tricky problem. Check this out. If you try to plug x equals 1 directly into this function, you get 1 minus 1 on top and 1 minus 1 on the bottom. That's 0 divided by 0, and in math, that's a huge red flag. It's undefined. So the function doesn't technically exist right at x equals 1. But that just leads to a way more interesting question. What value is the function approaching as it gets incredibly, incredibly close to 1?
So we can't land exactly on the number 1. But what if we just sneak up on it? Let's get really close. If we come from the left side, with values like 0.9, then 0.99, then 0.999, look what the function's value is doing. It's getting closer and closer to 0.5. And you know what? The exact same thing happens from the other side. Coming down from 1.1 to 1.01 to 1.001, the function is clearly, absolutely homing in on that same target, 0.5.
And here's the cool reason why that happens. Our function, f of x equals x minus 1 over x squared minus 1, can actually be simplified. See, the denominator, x squared minus 1, is what we call a difference of squares. It's the same as x minus 1 times x plus 1. So we can cancel out the x minus 1 terms, which leaves us with just 1 over x plus 1, as long as x isn't 1. And now it's totally obvious. As x gets close to 1, the function gets close to 1 over 1 plus 1, which is 0.5. The limit is what gives us a way to find that value, even when the original function has that little hole.
You see, this whole idea of figuring out where a function is heading, even if it never actually gets there, that is the core intuition behind a limit. So let's go ahead and put a more formal name to what we just saw.
Okay, this is the intuitive definition of a limit. Now, it sounds a little technical, I know, but all it's really saying is this. The limit is L if you can guarantee that your function's value will be as close as you want it to be to L. And how do you do that? Simple, just by making sure your input x is close enough to your target a.
But here is the most crucial part. It's this tiny but absolutely vital phrase in the definition. The limit does not care what happens at the point a itself. We only care about how the function behaves near that point. It really is all about the journey, not the destination.
Just look at these two graphs. On the left, we've got a perfectly normal continuous function. As x approaches a, the limit is just the function's value L. Simple enough, right? But now look at the graph on the right. It's got a hole in it, just like our first example. And even though the function doesn't even exist at a, the limit is still L, because that is the value the function is heading towards from both sides.
But for a limit to exist, there's one really important rule. The function has to be heading to the exact same place from both directions. Think of it like two friends trying to meet up at a specific spot.
Let's take a look at what's happening right at x equals 2 here. If we approach from the left side, just follow the line, where are we heading? It looks like we're heading to a y value of 3. Okay, but now what if we come in from the right side? Whoa, the function suddenly jumps down and starts approaching a totally different value, 1.
We actually have a name for these. They're called one-sided limits. The left-hand limit is 3, and the right-hand limit is 1. And since they are not equal, our two friends didn't meet up at the same spot, we have to say that the overall limit at x equals 2 does not exist. For a true limit to be found, those paths have to meet.
All right, so far our functions have always been approaching some specific number. But what happens when a function doesn't settle down at all? What if instead it just keeps growing and growing forever? This is what we call an infinite limit. And be careful here, it's not saying the limit is infinity. Infinity isn't a number you can actually reach. No, this is just our way of describing a function that just shoots up toward positive or negative infinity, growing without any bound as it gets closer and closer to a certain x value. When you look at it on a graph, this kind of behavior creates something called a vertical asymptote. It's basically a vertical line that the graph gets infinitely close to, almost like a wall that it can never cross or even touch, as it just rockets upwards or plummets downwards.
Okay, so we've got this kind of abstract concept of approaching a point or shooting off to infinity. But what's it actually for? Why is this one idea considered the very starting point of all of calculus?
The true power of the limit is that it gives us a mathematical microscope. It's the tool that lets us handle the idea of an instant, an infinitesimally small moment in time where it seems like nothing is changing, and still get a meaningful answer. It lets us zoom in on a single point with absolute perfect precision.
I mean, think about it. Without limits, there's no way we could define the exact slope of a curve at a single point. That's what a tangent line is. We can never calculate an object's velocity at one specific instant. And most importantly, we couldn't even create the derivative, which is the absolute engine of differential calculus.
So you see, the limit isn't just some abstract idea from a math book. It is the fundamental tool that allows us to mathematically describe and calculate the very nature of change itself. And that leaves us with a final, kind of provocative thought. If we can now analyze a single perfect instant, what questions that once seemed totally impossible can we finally begin to answer?